Hello and welcome to the lectures on state space approach to control system analysis and design. The topic of today's lecture is solution of state equations. This will also be continued in the next lecture. So far we have spent some time on development of mathematical models and expressing the mathematical models so obtained into the standard state space form. We also saw how to obtain transfer function from the state space description and how to convert transfer function backwards to a state space description. We had also seen the equivalent dynamical equations obtained through similarity transformations. Now, as we move to the solution of state equations, the basic motivation behind this is to understand the system behavior. So, we are given with the state equation in the standard form x dot equal to ax plus bu, in which x is an n-dimensional vector and the input u is m-dimensional vector. Initial state is specified at the time t equal to 0 as x0. Now we have to obtain its solution, which means determining the time response of the state variables for the time t greater than equal to 0 given the input. And once the state xt is known, then the output is easily obtained through this yt equal to cxt. We consider first the autonomous system, that is x dot equal to ax plus ax only, and the input is treated to be 0 or input is not applied. So we will obtain its solution, and of course the initial condition is specified at t equal to 0 only as x0. Even before we attempt obtaining the solution of the unforced system, we will consider the scalar system, that is the system with only one state variable, which is z dot is az, and the initial condition of the state z is also defined at t equal to 0 as z0. So the solution is expressed on the basis 1 t, t square, t cube, etc. as zt equal to b0 plus b1 plus b2 plus b3, zt equal to b0 plus b1t plus b2t square plus b3 t cube, etc. Essentially this 1 t, t square, t cube, etc. are basis, and b0, b1, b2, b3, etc. are the combining coefficients to obtain the solution zt. So we substitute this form of solution in this expression z dot equal to az. So on the left hand side we will have derivative time with respect to time of b0 plus b1, etc. this expression, and on the right hand side we have a multiplied by this assumed form of solution of z, a into b0 plus b1t, etc. Now this gives this expression in which the derivatives on the left hand side it was d dt of b0 which is 0, d dt of b1t which will be b1, d dt of b2t square which will be 2b2t, etc. So this is written here on the left, and this is what comes on the right. So in this what we do is we multiply, we equate the terms containing similar powers of t. So we have b1 equal to ab0 here, 2b2 equal to ab1, from which we will obtain b2 equal to half ab1, and in that this b1 will be substituted here as ab0, so we will get 1 by factorial to a square b0. Then this one gives 3b3 equal to ab2, from which we will get b3 equal to 1 by 3 ab2, and in that again B2 is substituted as this to obtain 1 by factorial 3 a cube B0. This we do for all the various coefficients, and so we have, after substituting those values in the expression for zt will be equal to 1 plus at plus a square by factorial 2 t square etc. whole thing multiplied by b0. At t equal to 0, the initial condition is given as z0. So in this we substitute z0 equal to this 1 plus a into 0, a square t, a square into 0 etc. So essentially we will have z0 equal to b0 or b0 equal to z0. And this is substituted in this expression to get this solution of zt. zt is 1 plus at plus a square t square by factorial 2 and so on multiplied by z0, and we recognize that this is e power at. So zt is e power at z0. This is the solution of the scalar differential equation. Having done that, now we proceed with the solution of the unforced state equation x dot equal to ax plus bu, and on similar lines we assume that the solution of the unforced state equation will be xt equal to b0 plus b1t plus b2t square etc., where these bi's are column vectors. Earlier they were scalar coefficients, but this time they are column vectors. Each column is of the same dimension as of x. We proceed with this. So we differentiate. So x dot becomes differentiation of b0 is 0, and b1t will give b1, b2t square will give 2b2t, and so on. So this, we have this, and we have x dot equal to ax. So in that, x dot equal to ax, in that we substitute x as this assumed solution. So we will get a into b0 plus b1t etc. Now we have two expressions for x dot. One is this and other is this. So we can compare the different terms, and by comparing we will obtain b1 as a b0, b2 as half a b1, which is, after substituting b1 in place of this half a b1, we will get 1 by factorial 2 a square b0. b3 will be obtained as 1 by 3 a b2, and again b2 is substituted in terms of b0, so it will give 1 by factorial 3 a cube b0. This we do with all the terms, and we substitute the things so obtained into the expression for xt which was assumed here. The values of b0 etc., b1 etc. is substituted in that. So then we obtain xt as b0 plus a b0t plus 1 by factorial 2 a square b0 t square etc. In this we substitute the initial condition. Xt at t equal to 0 is specified as x0. This is given. So once we put that x0 here, and on the right hand side t is 0, so this term becomes 0, this term becomes 0, this term becomes 0. So we get b0 equal to x0. We get this. And this we substitute in the solution of x, which was shown in the previous slide. So we'll get xt equal to this expression. x0 plus atx0 plus 1 by factorial 2 a square t square x0 etc. And in that we take x0 common on the right, leaving other terms together as xt equal to identity matrix plus at plus half 1 by factorial 2 a square t square etc. We see that these things are similar. This is very similar to the exponential e power at. So in which small a was a scalar. So it gives us a ground to us to show this infinite series as e power capital A into t. We introduce this matrix exponential e power at, and in that case xt can be written as e power at into x0. This comes from this. Xt is this into x0, and this is written as matrix exponential e power at. So we get xt as e power at x0. So it is to be observed that this matrix exponential e power capital A into t and the scalar exponential e power small a into t have several similar properties. For example, both are non-similar for all t less than infinity. Other property is that the product of two scalar exponential e power a t1 into e power a t2 is e power a t1 plus t2. Similar is with this, e power capital A t1 into e power capital A t2, it gives e power a t1 plus t2. Similarly, e power small a t inverse is e power a minus t, and so does the matrix exponential. E power at inverse is e power capital A minus t. E power small a t power n is equal to e power a into nt, and so does the matrix exponential. E power capital A t power n is e power capital A nt. So this e power at is called as the state transition matrix. It relates the state at any arbitrary time t with the initial state like this, and it is given the notation phi t. So phi t is essentially e power at, and this holds good in case of linear time invariant systems. In case of time varying system, phi t is to be obtained in much more difficult ways. So once we have phi t equal to e power at xt, the state at any time t, any arbitrary time t, is expressed phi t into x0. So we see that we see a few properties of phi t, and all these properties can be proved from this expression for phi t equal to e power at. It can be proved that phi 0 is identity matrix I. If we substitute 2 equal to 0 everywhere, we are left with I. We can see that the product of STM evaluated at T1 and STM evaluated at T2 is equal to STM evaluated at T1 plus T2. We can also prove that inverse of the STM evaluated at time t is same as STM evaluated at time minus t. We can also prove that STM evaluated at time t raised power n is equal to STM evaluated at time nt, whereas n is an integer, and derivative of phi with respect to time is equal to a times phi. These properties all can be proved using this expansion, phi t as identity plus at plus 1 by factorial to a square t square, etc. Now we consider the force system. X dot ax plus bu. Earlier we had considered the homogeneous system. So we consider now the force system. Now the input u is applied. And of course we continue with the initial condition specified at t equal to 0 as x0. So in this, what we do is we rewrite this. We take axt on the left side and we rewrite it like this. And we multiply all its various terms by e power minus at. So we have e power minus at x dot minus e power minus at axt equal to e power minus at but. And we recognize that this whole thing is first derivative of e power minus at xt. So we do that. We express the left hand side as d dt of this product e power minus at into xt, which is equal to this right hand side e power minus at but. And integrating both the sides, we get e power minus at x tau between 0 to t will be equal to definite integral from 0 to t e power minus a tau b u tau d tau. The lower limit was taken as 0 because the initial state is specified at time t equal to 0. So the equation which we obtained, this one, we can see that this left hand side evaluate at t and evaluate at t equal to 0, it gives two terms e power minus at xt minus x at t0, which is x0, and this is the integral on the right. And we rearrange it by taking x0 on the right and multiplying throughout by e power at. So we get xt equal to e power at x0 plus 0 to t e power at minus tau b u tau d tau. What we have done is, when it was multiplied by e power at, the integral, it became e power at e power minus a tau, etc. And because this can be taken inside, so it was taken inside the integral e power at e power minus a tau, and then it became e power a t minus tau, this one. Hence xt gets expressed as this, in which we have denoted e power at by phi t and e power a t minus tau by phi t minus tau. So we obtain the solution into this form, xt equal to phi t x0 plus 0 to t phi t minus tau b u tau d tau. And if it is multiplied throughout by c, yt is cxt, and so expression for yt becomes this. So having obtained the solution of state, it is straightforward to obtain the time response of the output yt. Now we consider the forced response in the situation when initial condition is specified at arbitrary time t equal to t0. Earlier we had initial condition specified at the time t equal to 0. So now we are given the initial condition as xt at t equal to t0, which is xt0. And now we have to obtain the forced response. So we bring the earlier expression. When the initial condition was specified at t equal to 0, then the solution was obtained as this. Xt was e power at x0 plus 0 to t e power at minus tau b u tau d tau. So from this, what we do is we try to get x0 in terms of xt0, and then we proceed. So in this we substitute t equal to t0, and it gives xt0 equal to e power a t0. Mind it, at place of t we have substituted t0. Here also in place of t we substituted t0, and so on. So we get an expression of xt0. This we can substitute in the we can pre-multiply. So what we are doing is we are pre-multiplying by inverse of this on all the terms. So we get e power minus a t0 x t0 equal to, it will become, see, this e power a t0 x0 multiplied by e power minus a t0 will lead to identity, and we will be left only with x0. And e power a t0 multiplied by this will lead to cancellation of one of the terms, and we will be left with only e power minus a tau. So this becomes equal to this, and from this x0 is obtained as this minus the integral, which is like this. This expression of x0 can be substituted in the place in this one. This x0 is substituted in this one to obtain this expression. Xt is e power at, e power minus at0, xt0 minus, again it was containing two terms, so this multiplied by e power at, this multiplied by e power at, this and this are here, and this integral was as it is brought here. We do little manipulations. So what we do is that the first term, this gives e power at into e power minus at0 gives e power at minus t0, which is written here, and this e power at goes inside the integral to give e power at t minus tau, it will give, and this one we have broken into two integrals, one from 0 to t0 and other from t0 to t, like this. So we recognize that this one and this one will cancel with each other. These two cancel, leaving this one here and this one here. So xt is obtained as e power a t minus t0 xt0 plus integral t0 to t e power a t minus tau bu tau d tau. This is the solution of state xt given the initial condition at any arbitrary time t0. We denote Ea t minus t0 as phi t t0. Similarly, Ea t minus tau as phi t tau. And in case of linear time invariant system, phi t t0 will be phi t minus t0. Similarly, phi t tau will be phi t minus tau. So this part we see carefully. In this, input doesn't appear, and in this part we see that initial state doesn't appear. So this first part in which the input doesn't appear, this makes one component of the solution, and this is called as the zero input response, the response of the system in the absence of applied input. And this part in which the initial state doesn't appear is known as zero state response, or the response of the system in the absence of initial condition. So the total response xt is summation of zero input response and the zero state response. Another observation we make is that this both the zero input response, which is this, and the zero state response, which is given by this integral, both contain the STM phi t t0 here and phi t tau here. So knowledge of state transition matrix STM is absolutely important for determining the time response solution of the state, and because output is determined by pre-multiplying state with the output matrix C, so the determination of time response of output is also absolutely, it becomes absolutely necessary to know the state transition matrix before we can obtain the time response solution of state or the output. So we need to spend some time on how to determine the state transition matrix, and this will be the topic of our next lecture. With this, we close today's lecture. Thank you very much.